Hi, in this video I'm going to go over how to write answers to the Achievement Standard 91166. That's the 2.6 Chemistry exam for the NCEA assessment. It's a 2024 exam paper. So remember, Achievement Standard 91166. Okay, so let's have a look. There are 3 questions in the paper. Each question is marked out of 8. This is question 1. So Tiwai Point in South Island of New Zealand extracts large amounts of aluminium sourced from an ore called bauxite, which contains the mineral aluminium oxide or aluminium 3 oxide. One step of the extraction process is as follows, and they've given us an equation here, which is aluminium oxide plus sodium hydroxide gives us 2 sodium aluminium dioxide plus water. Now the graph shows the mass of aluminium oxide as it reacts with 5 moles of sodium hydroxide. So here's a graph here that they've given us to help us with this question, and they're going to ask us some questions about this graph. If we look carefully, because we take our time to unpack these resources, we can see on the left hand side they've told us that it is the mass of the aluminium oxide is on the y-axis and time is on the x-axis. It has been broken into 2 sections by a dotted line. Add a second line on the graph to predict the rate of reaction and mass of aluminium 2 oxide if 2 moles per litre of sodium hydroxide was used in the reaction instead. Assume both reactions started with the same mass of ore. Okay, so what they're expecting us to do on the same graph is to, with our pen, draw another line to show to sketch what an acid that is 2 moles per litre, that's 4 times as concentrated than the 0.5 moles per litre, how it would react with aluminium oxide and what the line would look like. Now, of course, what they are referring to here is that there has been a change in the concentration of one of the reactants. So we're looking at a reactant rates question, and we're already starting to think about how we're going to explain that. But the first thing we should know is if we have a more concentrated solution of sodium hydroxide, we're going to get more frequent collisions, so the reactions will happen more frequently, and therefore the rate of reaction is faster, and we have a steeper slope on our graph. So the initial part of our graph is going to be a steeper slope. Also, because we're using the same amount of aluminium same mass of ore, aluminium oxide, the bauxite, then we're going to start our line at exactly the same place. So we're going to draw a curved line similar to the one that's there, but it's going to start with a steeper angle and it's going to start at the similar place. And there, I've drawn an example here. Now, if we did that correctly and we met those requirements, they would give us our first achieved grade. Now, remember, we're trying to accumulate a number of achieved grades, a number of merit grades, and a number of excellence grades. And based on how many you get of each depends on what you'll get for the paper and the mark that you get. Okay, with reference to the line that we've just drawn, explain the effect the change in concentration from 0.5 to 0.2 moles per litre would have on the rate of this reaction. Okay, so here they've actually given us some more help here, and they've said in your answer you should include the mass of the aluminium oxide, each section of the line, and collision theory. Well, I'm going to start by, let's state about the mass. Okay, so both lines start at the same point as they both react with the same amount of aluminium oxide. The added line shows a steeper decline in mass due to the higher concentration. Now that hasn't given them a lot of detail here, but we have ticked off the first bullet point here. The next thing that we're going to do here, and actually to get the first achieved point, I had to have said that the mass starts the same, and also identified that the reaction rate is going to be faster for the second line. But let's explain why now. So what happens is, if we have a higher concentration of sodium hydroxide, we have more particles per unit volume of sodium hydroxide. Therefore, there is a higher frequency. It is more likely, but we use the terminology higher frequency, that there will be collisions with the aluminium oxide. That is, the sodium hydroxide and the aluminium oxide will collide more frequently. Because they collide more frequently, more of those collisions will be successful per second, and the mass of the aluminium oxide is removed more quickly. We see a steeper gradient. So I've referred to the graph, and I've used collision theory to explain why the higher concentration is reacting faster. Maybe I should say something about the different sections. Let's look at section B compared to section A. Why is the rate of reaction decreasing in section B? Well, let's just state something about that to make sure we cover all of the 3 points they've asked us. So the section B is, we should have said that the concentration of sodium hydroxide is decreasing as it reacts. So as the concentration decreases, we get less frequent collisions, producing a slower rate of reactions. So because the sodium hydroxide is used up in the reaction, as the concentration decreases, we get a lower reaction rate. Now, how did they mark this? Well, if you correctly linked the concentration to the increase in frequency of successful collisions, like I did here, that's a merit. If you also did a correct comparison between sections A and B, okay, you could have said the reaction was completed quicker in reaction B. That could have also been another bit, or the comparison is, we said here, our comparison is the reactions happening less frequently because there's less sodium hydroxide around because it was used up. To get an excellence in this part of the paper, you needed to carry out all of the things that I've covered up the top here. You should have used collision theory to explain why the 2 mole per liter was faster than the 0.5 mole per liter. And you should have made a comparison between section A and B, and you should have linked it to both the line and the rate of reaction. So here, the total grades that you could have got, there were 2 achievement opportunities, 2 merits. Remember the 2 merits, one was explaining collision theory and one telling us what the difference was between the section B and the section A. Excellence was covering all points. Okay, let's look at the part B here of this. So that was part A, the first question. Part B, they've said, well, what if we took a 0.5 mole per liter solution of sodium hydroxide, can we carry out a calculation to find out the hydronium ion concentration? Okay, so what we need to assume here is that the concentration of the hydroxide is equal to the concentration of sodium hydroxide. And we need to realize that when we know the concentration of the hydroxide, we can't calculate the concentration of the pH until we've converted that to the concentration of hydronium ion, H3O plus ion. So we're going to use this equation here at the bottom first. The equilibrium constant for water, Kw, 1 times 10 to the negative 14 equals the concentration of hydronium ions times the concentration of hydroxide ions. Now, we need to remember that these 2 equations are given to us on the resource sheet of the exam paper. We're going to use the second equation and we're going to rearrange it. So what I did here is I divided, what did I do here? Yeah, I divided both sides by, so divided the left by the concentration of hydroxide and the right by the concentration of hydroxide. The OH's cancel off the right hand side and we're left with H3O plus equals 1 times 10 to the negative 14 over the concentration of hydroxide. Now you should have practiced this sufficient times in your workup to in this topic, so you're really familiar with, whenever you want to find the hydronium ion concentration, you just take the 1 times 10 to the negative 14 and divide it by the hydroxide concentration. It's also true that when you want to find the hydroxide ion concentration, you take 1 times 10 to the negative 14 and divide it by the hydronium. Anyway, so we put the values in and we put this into a calculator and we get the answer 2.00 times 10 to the negative 14 moles per litre. That's quite a very low concentration. But if you remember how pH is related to the exponential number here, we can see because this is a negative 14 and this isn't 1, the pH is going to be 13 point something. And 13 point something is a reasonable pH for something that we consider here as a strong base. Now let's actually calculate this pH. So we're going to put it into our calculator, and we're going to press the minus and the log button and then place this number in and press execute. And the answer you get is 13.7. Now actually for this very first one here where you had to substitute and rearrange the equation, that was an achieved grade. For the second one, if you forgot or if you didn't do this and you just took the pH using the concentration that you were given, you could have got an achieved grade in part 2. But if you got the correct answer, 13.7, you got a merit grade. Okay, part C. So we're still using the principles of collision theory and particle theories to explain why catalysts would help increase the rate of production of the sodium aluminium salt. Now the sodium aluminium salt is the product of the reaction we had in the previous question. You should include an energy profile diagram to support your answer, and they should have had some practice drawing these. So let's draw one here. We've got the energy on the y-axis, and on the x-axis we've got reaction as it proceeds. I draw the reactants and products. So this is very similar to the type of graph that we would have drawn in our achievement standard 91164, apart from we've put this activation energy hump here. Now I've drawn a full line here to show the activation energy, what it would be without the catalyst. And then I've drawn a dotted line to show an alternative path, and that is the activation energy with the catalyst. So this dotted line is our alternative path for the reaction, and then the double arrow here is showing the height of the activation energy with the catalyst. So what do we say about this? Well, that's what a catalyst does. A catalyst provides an alternative path that has a lower activation energy than it would have had. And it means that it's easier for the reaction to overcome the energy barrier or the activation energy barrier. So if we were to say that, well, okay, so this provides an alternative path with a lower activation energy, but how does that actually speed up the reaction? Well, what we would say here is because of this, more collisions that occur have the sufficient energy to overcome the activation energy, and there will be more successful collisions per second, and the sodium aluminium oxide or the sodium aluminium salt will be produced more quickly, so we'll speed up the reaction. Now if we were able to put both of those terms down, alternative pathway and lower activation energy, and draw this graph, they'll give us the merit. If we had just one of those terms, we'd get the achieved. If we were able to put that together and explain in this second paragraph I've written here, you've got the excellence. Now taking all of what we did on the previous page and this page, if you got 2 excellence grades, then you get an E8. If you get 2 excellence grades but you've made a small mistake somewhere, you'll get an E7. You needed 4 merit grades to get an M6 and 3 merit grades to get an M3. Apart from that, you count up your A's to get an A4, an A3, an N1 and an N2. Okay, let's have a look at the next question. Right, so let's have a look at question 2. Question 2 is another industrial chemical operation that happens in New Zealand here. It's a superphosphate fertilizer is manufactured in New Zealand using phosphorite rock and sulfuric acid. The sulfuric acid often produced on site and includes a reaction involving oxygen gas, sulfur dioxide gas and sulfur trioxide gas, which is represented by the equilibrium expression below. So here they've given us an equilibrium expression and they've given us a Kc value of 32.7 at 25 degrees Celsius. Now remember that always, if they give us a Kc value, it's always going to be given at a specific temperature because it is temperature dependent. So they want us to write the equation for which this Kc is true. Now, if we remember that the Kc equals the product terms over the reactant terms, and the exponents in the Kc are actually the coefficients in our equation. So if we were to write this out, SO3 here that is on the top would be the only product, and it would have a 2 in front of it. SO2 would be a reactant with a 2 in front of it, and O2 would also be a reactant. And that is true, and this is the equation we get here. 2SO2 plus O2 goes to 2SO3. This reaction is set up and allowed to reach equilibrium. Okay, so they've put the mixture in there and let it reach equilibrium, and they've calculate the concentration of oxygen at equilibrium. So we're going to use the Kc expression, we're going to substitute in values and find the unknown. The unknown is O2. So let's put this into our equation here. Here we've got 32.7 equals, so the first step, substituting into here, we just substitute our numbers into the values, the values into the algebraic symbols we're given. And then the second step is to rearrange and solve. So I rearrange it here and I solve to find that the answer is 0.265. Now, if I just go back to this part 1 here, if we got this correct, we got an achieved. They said in the paper we didn't have to give the states that they were gases. I would always recommend you do that. You never know for any given year whether they're going to actually expect you to have done that to get the mark. When we do the second one, they would have given us achieved grade if we substitute the values in the correct places and had put their exponents. You would be surprised how many people forget to put the exponents in from the coefficients. That is the most common thing. And then the next most common thing is actually carrying out that calculation with the correct exponents. Anyway, answer 0.265. If you got that correct, you got a merit. Didn't have to put the correct number of significant figures in because this isn't an excellence question. Now the next one says, if they set up the reaction differently with concentrations of each component indicated below, so they've got us 3 concentrations, they want us to calculate if the setup with these 3 concentrations would be at equilibrium or not. So here's the rub. Here's what happens. If we substitute those 3 values in, sulfur dioxide, oxygen, and sulfur trioxide, and carry out the calculation, and it equals 32.7, then that means that the system or the reaction is at equilibrium. If it doesn't, it means it's not at equilibrium. Now, in fact, it's when we do this calculation, it's not called the equilibrium constant because we assume this is not going to be at equilibrium. So you'll see that I'm just going to write this like this. I'm going to put equals. I'm just going to leave it blank here because the number is, we haven't defined it a value yet, but we are going to get a number, and we're just going to compare it to this number of 32.7. So I've substituted in the sulfur trioxide at the top, the sulfur dioxide at the bottom, and the oxygen in the bottom, and then I've carried out the calculation. And the calculation that I get, the answer is 1.93. No unit. Now we need to compare this to the Kc. Does this equal the Kc? No, it doesn't. We expected that because that's why they gave us the question. So because it doesn't equal the Kc, it means it's not at equilibrium. And we should state that. The value is lower than the stated Kc, so the reaction is not at equilibrium. So this is an achieved to do the correct calculation and to be able to identify that it's not at the Kc value and it's therefore not at equilibrium. You get a merit there. Okay, so explain what must occur for the equilibrium to be established. Okay, so I'm just going to put this statement here again. The value is lower than Kc, so it's not at equilibrium. So if we want the equilibrium to be established, we need to make this value larger. So Kc is larger, and the important thing here is that Kc is actually an expression that represents the concentration of the products over the concentration of the reactants. So in order to get a larger number than 1.93, to get closer to 32.7, I'm going to have an increase in my products concentration and a decrease in my reactants concentration. And I should write that down clearly. So I've put for a start that Kc equals reactants concentration over products concentration. In order to create more products, the Ford's reaction is favored to increase the concentration of the products and decrease the concentration of the reactants. This increases the value of Kc and of the unit, or of this, increases this value until it reaches Kc or matches Kc. So here, this is an excellence question. So the excellence question is, the points are really going to come about from, okay, were you able to say that the Ford reaction is favored? Yep. Okay, we'll give you an achieve. Can you say that by favoring the Ford's reaction, it would produce more products and less reactants? Merit. Can you say, but because of that, it will increase the value and it will be closer to Kc? That's the excellence. Okay, so the sulfur trioxide, they've taken it from the previous reaction and they're now going to make sulfuric acid. And it says sulfuric acid can be manufactured using the following reaction, and it's got sulfur trioxide is added to water to make sulfuric acid. Use equilibrium principles, identify then describe the effect on the position of the equilibrium. And the first one we're going to have to explain here is when water vapor, H2O gas, is added to the reaction mixture. Okay, so we're using Le Chatelier's principle. We look at the equation and we see that water is a reactant. If we add more of the water vapor, we are changing the system. That's a dynamic equilibrium, and it's going to want to oppose it using Le Chatelier's principles, which is it's going to do whatever it will oppose the change by getting rid of the change that we've made. So we added water, it's going to remove the water until it reestablishes the relative concentrations of the products and the reactants it had in the first instance at the start at equilibrium. So we need to write that down. So how do we, the Ford reaction is favored. So as H2O is added, the reaction at dynamic equilibrium will oppose this by making more water. The Ford's reaction that removes the water in order to re-establish the relative ratios of reactants and products will be favored. Now this, to re-establish the relative ratios of reactants and products, it's a really strong phrase if you understand that. The ratio of the products to the reactants has to be re-established if something is at equilibrium. Okay, and we do, that's the reason for this. And that ratio is really just the Kc. Okay, so what about the second part? Well, the second part is we added sodium hydroxide. Well, this one's a bit confusing for a start because there is no sodium hydroxide in the equation. It's confusion until you remember, oh, sodium hydroxide is a base and sulfuric acid is an acid. So what actually sodium hydroxide does is it reacts with the sulfuric acid and it removes it from the equation. So if you take away the sulfuric acid in the form it's in the equation, it can no longer carry out the reverse reaction. So the Ford's reaction will be favored. So we need to state that down. Ford reaction is favored. The added sodium hydroxide will neutralize the sulfuric acid and remove it from the reaction. As the sulfuric acid is removed from the system that's at dynamic equilibrium, it will oppose this change, that's Le Chatelier's principle, by making more sulfuric acid. The Ford's reaction will be favored, the one that makes more sulfuric acid. Okay, if you can identify, or if you can write one of these correct, get one of these correct, then you're achieved. If you can explain one of these, so if you can get the correct direction that it will favor the Fords, then you're at achieve. If you're able to say that, give the explanation, then that's a merit grade here. Okay, so oh sorry, no, that's not correct. So in this case, it is, if you are able to explain one of these correctly, that's achieved. If you're able to get either of these correct but give the reason for the shift, then you're at merit. That's a bit ambiguous, that question. Look, usually you would expect that this was an achieved merit excellence mark. In 2024 it wasn't. They'll give you a merit if you explain one of these thoroughly, or if you partially explain one, they're going to give you an achieved. Here's the next bit of the question. The reaction can be performed under high pressure. Explain why this is beneficial to the manufacturing process. Okay, so something that is beneficial to a manufacturing process means they're going to produce more of the products. So we're going to have something that favors the forward reaction, but do we understand why? Okay, we know that when we put things in a high pressure environment, it will move towards the side that has the least moles of gas particles. Now we always use the term moles of gas particles. It's important there. So we can see that there are 2 moles of gas particles on the left hand side and 1 on the right. So we just need to explain these details down. If the pressure is increased, it's going to oppose this. Remember, always put this statement in, oppose the change. That's Le Chatelier's principle, by favoring the reaction direction that produces the least gas particles. There are 2 moles of gas particles on the reactant side and 1 on the right. So the forward reaction is favored as it produces less gas particles. So more sulfuric acid will be produced. Producing more product is a benefit to the manufacturer. So that's achieved, merit, or excellence. So if you identify it will favor the product, therefore you get an achieved grade. If you can explain that it favors the side with fewer gas particles, okay, then that's your merit. If you can link it to fully justify it by linking it to the example you're given, it's a manufacturing process, it will produce more sulfuric acid, you're at excellence. So for this question, this is this slide and the previous one, if you got 2 E's correct, you're at excellence, right? If you got 2 of them correct but there's a little mistake, you might be at E7. To get an M4, you get an M6. If you have 4 M's, you get an M6. If you have 3 M's, you get an M5. And then for every for 4 achieves, you'll reach the A4 requirement. 3 achieves A3, 2 achieves the N2, and 1 achieves the N1. Right, let's look at the last question of the paper. So here we're looking at an acid-base reaction, obviously. So it's a reaction of HSO4 minus as shown below. We can see HSO4 minus is reacting with carbonate ion to produce a sulfate ion plus this hydrogen carbonate. In question 1 is identify the species acting as acids and the species acting as a base. That is the reactant, that's the acid, and the reactant, that's the base. In the above equation and their conjugate pairs. Okay, that's cool. So we remember that to be an acid, you have to donate a proton. That's Bronsted definition of an acid. Now, if we look at these 2 species, only one of them actually has a hydrogen. So that one's going to be the acid, but let's check. If this gives away its acid, it turns into the sulfate. That's correct. It's lost its acid and it's lost a positive charge. So these 2, this must be the acid on the left-hand side, and this must be its conjugate base on the right-hand side. Those 2 are the conjugate acid-base pair. So let's write that in, hydrogen sulfate, and then we have sulfate ion here as our conjugate base. That means that our carbonate must be a base. Is it accepting a proton? Yes, it is. It's getting it, and it's becoming this hydrogen carbonate on the right. So these 2 are our base conjugate acid pair, and we put those down in our answer. Excellent. So they're going to give us an achieve for that. This is a skill, again, you should practice, make sure you're proficient with it. The next thing, well, they're asking us again to do something with a KC. They want us to give the expression. Okay, so KC equals product to equals the terms for the products multiplied by the terms for the reactants. With their coefficients as exponents, but the coefficients are all absent from here. They're all 1, so we don't need to worry about exponents. So it's just SO42 minus concentration times hydrogen carbonate concentration over hydrogen sulfate concentration times carbonate concentration. Okay, that's nice. It's an easy way to pick up a grade. Okay, so the next bit's a wee bit harder. The reaction was initially performed at 25 degrees Celsius to determine the Kc value. When the reaction of temperature was increased to 50, the Kc value increased. Okay, so the Kc has increased with temperature. Well, that kind of makes sense that it would change with temperature, because Kcs are only true for the given temperature. They are dependent on the temperature. They're temperature dependent. So explain whether the forward reaction is exothermic or endothermic. Okay, so here's our argument. Because the temperature increased, the reaction is going to oppose that change. Because this is a dynamic equilibrium situation, here's a double arrow. This is Le Chatelier's principle. So if we temperature increase, it want to oppose. Now, how does it oppose that? Well, it uses the endothermic direction of the reaction, because that will remove the heat that you've added. Okay, so the endothermic is going to cool it down, the opposite to heating it up. So what we know is if the Kc increased, the endothermic direction is going to be favored. Now we know that the endothermic direction is favored. We can then say that there must be more, because, sorry, this is a different argument, because the Kc increased, and remember the Kc is the products over the reactants, we must have had an increase of the products and a decrease in the reactants. And if we have an increase in the products and a decrease in the reactants, that only happens when a forward reaction is happening, right? Because the Kc increased, we have an increase in products and an increase in reactants, so the forwards reaction is happening. Therefore, the forward reaction that produces the products must be favored, and this must be the endothermic reaction. So we've got two different bits of information we had to pull apart here. The first one was that the Kc got larger. The Kc got larger because there were more products because we produced more products compared to reactants, right? So the forwards reaction was favored. We also knew here that the temperature was increased, and remember what we knew is that to oppose this change, the endothermic direction must have been happening. So the endothermic direction happened, but we also know that the forward direction happened, so the forward direction must be the endothermic. This is a very tricky question, and in fact they give you an achieved 2 merits and an excellence here. So if we can explain the Kc explanation, right, that the Kc got larger, therefore the forwards reaction is favored because more products are made and less reactants, that's a merit. If you explain that the endothermic reaction must be favored because the temperature was increasing and the endothermic is the type of reaction that will remove the added heat, that's the other merit. If you gave both, you had excellence for that. Well done, you. Okay, so next part, solutions of 0.1 mole concentrations were made each of the following. Okay, so they've given us some acid, but this is an acid-based question. They've given us 3 solutions. Can you recognize which ones are acids, bases, or if it is an acidic salt or an acidic base? Okay, so the pH of each. Explain the pH of each. Okay, so we need to identify one and explain the pH. This is on the harder end of the spectrum of these types of questions, but we can do it. Okay, so the first one, NH3, you should have seen a few times. You should have practiced this, and you should be familiar with it. It's ammonia, and ammonia is a weak base. Now, because it's a weak base, the first thing we're going to say is it partially dissociates when placed in water. Remember, what that means is it sets up an equilibrium with water in which only a small amount, only a fraction of the reactants are turned into products at any given time. We draw the equation for it acting as a weak base. Okay, so remember it's acting as a weak base, it's accepting a proton, we're making hydroxide. Because this is at dynamic equilibrium, we only get a low concentration of OH-, because it partially dissociates, only a small concentration of OH-. So therefore its pH is correspondingly, it's a base, but it's not a strong base, it's a 9 to 10. Okay, so what's the next one? Next one, HNO3. We should recognize this as being nitric acid and know that it's a strong acid. Because it's a strong acid, it is going to fully dissociate when placed in water. When we draw its equation, it's going to have a single arrow. Okay, and it's making the nitrate ion and the hydronium ion. Because it's a single arrow, all of these acid particles are turned into hydronium particles, and it will have a high concentration of H2O plus, of excess H2O plus. I use the word excess because there's always a concentration of OH minus or H2O plus in water, but this is producing more of it. But it's a really high concentration, so therefore its pH is going to be somewhere around about 1 to 2. Okay, let's have a look at the last one of these three, and that's NH4Cl. Okay, so NH4Cl, you should recognize that NH4Cl breaks into NH4 plus and Cl minus, and you should recognize that NH4 plus is the conjugate base of ammonia, NH3, so therefore it's going to be a weak acid, because the conjugate base of a weak base is a weak acid and vice versa. You also might know that chloride ion, because it is the conjugate base of a strong acid, well, it's neutral, it's neither acid or base. Anyway, so the first reaction we do is this, dissociating in water. Because it's a salt, it's going to break apart completely into NH4 plus and Cl minus. It fully dissociates when we place it in water. Now, because remember we said the Cl minus, it doesn't react with water, it's neutral, but the NH4 is a weak acid, so we're going to draw it. We're going to say it partially dissociates when put in water, and we're going to draw its reaction. Because it's partially dissociating, it's got this double arrow, and it's turning back into some ammonia and some H3O plus. That makes it acidic because it's producing hydronium ions, but because it's only partially dissociating, it's a lower concentration of hydronium ions, so it's going to have a pH that is larger than a strong acid because it doesn't have as high a concentration of H2O plus. So this produces a low concentration of excess H2O plus ions, and so it has a pH of 4 to 5 because it is an acid, but it's not a strong acid, it's a weak acid. So the last question in this paper is they want us to do here, part 2, discuss the conductivity of these three. So if you remember what before we do that, let's just give the grades that we get for these. There's 2 achieved grades, and the achieved grades were pretty much, if you identified 2 of the pHs correctly, you got an achieved. If you were able to put 2 correct balanced equations, you got an achieved. If you can explain the pH of 2 of them using the correct equations, often that's the first 2 because those are the easiest, the weak acid, weak base, strong base. You get an excellence if you got all of it correct, and that means explaining the acidic salt or the acidic base. Oh, sorry, acidic salt or acidic base, basic salt or the acidic salt. Okay, so last question here, discuss the conductivity. Well, conductivity is solely dependent on the ability of a substance to conduct electricity. Conductivity, I see that. When they say conductivity, obviously they're referring to conductivity of electricity. So it's, can you transfer a charge? Now, the only things that can transfer charge are particles that have charges in themselves. Those are electrons if it's metals, but it's ions if it's a molten ionic solution, or if it's an aqueous ionic solutions. These can produce aqueous ionic solutions or solutions with ions in them. But the very first thing we should state is these are only going to conduct if we have charged particles. And here it's 3 things we need to make sure remember. Explain the requirements for a solution to conduct electricity. Okay, there are charged particles that can move freely. Compare the extent of conductivity of each. Well, the ones that have the most charged particles will conduct the best, and refer to relevant equations. So a solution conducts electricity well when it has a high concentration of free moving charged particles. Those are the ions in solution. Both HNO3 and HCl fully dissociate when placed in water. Okay, as we saw in our first, as we saw in this equation here and the one on the previous slide. So they have lots of ions available to conduct charge and are good conductors of electricity. NH3, however, only partially dissociates in water. So it has a low concentration in NH4 plus and OH minus produced, so the concentration of ions are low, and it's a poor conductor of electricity. So this one here has 2 achieves, 2 merits, and an excellence. A bit overboard here, but hey, it is what it is. So if you said a correct statement about conductivity, about the conductivity of 2 solutions, if you said that, if you said one conducts well and one doesn't, or this one conducts well and another one does, you get an achieve. If you defined conductivity correctly, you get an achieve. If you had a correct statement relative to the concentration of species linked to the conductivity of 2 species. So if you got 2 of the answers correct, let's say that you explained the nitric acid conduct really well because it had a high concentration of ions, because it fully dissociates, and you said ammonia didn't conduct well because it only partially dissociated, it had a low concentration of ions. That's a merit. Okay. Also as a merit is if you connected the conductivity to the extent of dissociation. So if you had used the word dissociation in there correctly, that's a merit point in itself. So if you just said, okay, look, nitric acid has lots of ions in solution, that's why it conducts well, that's a merit. But if you'd also, if you'd said that about ammonia as well, the correct statement. But if you would have got another point if you'd explained that it's to do with the fully dissociation, the partial dissociation of the the chemical in the solution. Excellence, you got all of this right. Kind of messy marking here, very generous if you did it well. Can be really hard when you didn't do it well, if you missed this part, or if this wasn't your strongest part of this whole standard. You can get pretty well punished here because you lose 2 merit grades and an excellence. Anyway, what they did here is if you got overall 2 E's, you got an E7. If you got 3, you got an E8. You need to get 4 merits to get an M6, 3 to get an M5, and then again with N1, N2, A3, A4, it's 1 to 4 A's. So from the 3 questions, if you take the grade that you got from the 3 questions and you add it up, if you got between 0 and 7, you didn't pass. More practice needed. If you got 8 to 13, you've passed. If you got 14 to 18, that's pretty good. Okay, you're doing pretty well at this standard. You should be pretty happy with that. That's a merit. And if you got 19 or more, you're at excellence grade, and well done you. You're amazing. Look, if you're starting to get the handle of this by practicing these exams and looking at this video, then go back and look at the one I did for 2023 and 2022. Just the more that you expose yourself to the ideas and to the questions, the stronger that you will get in your actual exam, or the better mark you'll get in the exam, and the stronger answer in your exam. The more practice you can do in different ways, the better you'll be. Best of wishes with your exam, and I hope it all goes well for you.